All right. Thank you all for showing up again to another edition of the High Energy Lunch Talk in the age of the pandemic. We have our first speaker is Satoru Katsuda.
Peter, hang on.
Yes.
Sorry, we flipped the speaker. We flipped.
Oh,
the
you're right. You're right. We are not
yeah.
first. Sorry.
Sorry about the confusion, everyone. We have had a lot of changes to our schedule this week. Actually, if you were following our calendar from before, you'll know that we actually had a different speaker who had to cancel last minute, and then we found a new speaker, and then we had to switch around schedule. So thank you for putting up with all the confusion, and thank you for being here. So our first speaker today is Arnab Sarkar. Thank you for joining us last minute. He stepped up as of last week to give us a talk this week. So hello, thank you. He completed his master's degree at the Presidency University in Kolkata in India, and then moved to the US to pursue his PhD at the University of Kentucky. He is also now an SAO pre-doc fellow. He's working on his PhD thesis with Dr. Yun Su, who several of you might know because she was here a while ago, and is a pre-doc now with Dr. Scott Randall. So hi, and please go ahead and share your screen and take it away.
Okay. Can you see my screen?
Yes.
Okay. And can you hear me loud and clear?
Sounds good.
Okay. Okay, so thanks for the nice introduction, and hello everyone. So I will try to divide my talk into two phases. In the first half, I will talk about the gas properties of a cool core galaxy group MKW4 out to its virial radius. And in the next half, I will present some new results on the metallicities of two galaxy group. The one is the MKW4, and another is a non-cool core galaxy group, Antilia. So we know from the standard CDM structure formation model that clusters basically grow and evolve via mergers and accretions along the cosmic filaments. Now, these basically leave a distinctive marks on the gas in the outer regions of the galaxy clusters. So probing that gas properties at the cluster outskirts, that basically offer a powerful approach in understanding the cluster growth. Now, the outskirts of the galaxy groups are comparably unexplored because of their low surface brightness compared to the massive galaxy clusters. But the studies of the massive galaxy clusters have recently brought up some unexpected results, like flattening of entropy profiles beyond R500 compared to what is expected from the gravitational collapse only model. So as an example, this famous plot in the Stephen Walker 2019 paper that shows that scaled entropy profiles of a number of clusters with different masses. Now you can see that entropy profile of the massive clusters, which is actually the red one, um, that falls below the gravitational collapse only model, which is this black line, and where at the outskirt regions, and where the low mass clusters, which is the black one, or the galaxy group, that stay aligned with this gravitational collapse only model at the outskirt regions. So there's several explanations like thermal non-equilibrium between electrons and ions, unresolved cool gas clumps have been proposed to explain such deviation at the outskirts for the massive galaxy clusters. But for a long time, people thought that the gas properties of galaxy groups to be a scaled down version of the massive galaxy clusters. But from this figure indicates that the physics of the galaxy group at at the outskirts are a bit different compared to the massive clusters. And also the metal enrichment processes in the galaxy groups are an open question because the deep gravitational potential well of massive cluster that helps to hold all the metals that ever produced by the star inside their virial radius. But the shallow gravitational potential well of galaxy groups that makes them more vulnerable to non-gravitational processes, just like galactic winds and AGN feedback that driven by the supernova. So these can expel much of the metal enriched gas out of the galaxy groups. So these are the reason that motivates us to probe the gas properties and the metallicity of the galaxy groups. Now, MKW4 is a cool core galaxy group at a redshift of about 0.02 with a global temperature about 1.6 keV. And here in this plot, in this figure, this is a Suzaku mosaic image of MKW4 in zero point 0.5 to 2 keV energy band. And this magenta circle here that shows the R200 of MKW4. Now, we use the Suzaku observation because, as we know, the typical surface brightness of the group at the outskirts falls below the 20% of the total cluster emission, and which makes the measurement of the gas properties extremely challenging. But Suzaku is an ideal exotelescope to measure these gas properties at the group outskirts because it's low particle background and a better spectral sensitivity below 1 keV. But there is a downside using the Suzaku, obviously, is that the Suzaku has a modest point spread function of like 3 arc on it. So Suzaku did not detect the faint point sources, which is very bad because it causes significant statistical and systematic uncertainty in the measurement of the gas properties. So what we did, we used the Chandra snapshot observations of MKW4 at the outskirt regions to resolve the point sources and constrain the cosmic extra background at the outskirt regions. And here, this is the Chandra mosaic image of MKW4. And these green tiny circles and ellipse, they actually represents the result point sources. So this is the surface brightness profile of MKW4 in 3 different directions because uh, that in the Suzaku observation, you can see that we observe MKW4 in 3 different directions, this north direction, east and northeast direction. So here we are showing that the surface brightness profile of MKW4 in 3 different directions. And this black line here is the best fit the beta model. Okay, now the left-hand side, this is the deprojected temperature profiles of MKW4 in 3 different directions, and which is derived from the Suzaku and Chandra observation. And you can see that around R200, the temperature at 3 directions are remarkably similar within their 1 sigma uncertainty. Left-hand side, right-hand side, this is the 3D entropy profile of MKW4 in 3 different directions. And here, this dashed line that represents the entropy profile obtained from the gravitational collapse only model. Now, you can see that between R500 and R200 are measured entropy profiles that align with this gravitational collapse only model. And this basically suggests that the gas dynamics at the outskirts of MKW4 is mainly regulated by the gravitational potential. And this is different than what we usually observe in massive galaxy cluster that I just showed you, that the entropy that falls below the gravitational collapse only model. So this well-behaved entropy profile of MKW4 at the outskirts basically is suggesting that MKW4 is relatively undisturbed system, and the merger rate is comparably lower because it has a very shallow gravitational potential well. Now, near the central region, we found the excess entropy compared to the gravitational collapse only model. And this entropy excess may be the result of the Asian feedback or galactic winds driven by the supernova at the center of the MKW4, and which basically pushes the hot gas towards the larger radii and making this entropy profile elevated at the central region of MKW4. So next, we estimated the gas mass fraction of MKW4 in 3 different directions. This is the plot for that. And you can see that gas mass fraction basically rises from the center and attains a value around 9% within the R200. Now, we also calculated the stellar mass of MKW4 using the 2-micron all-sky survey data, and which results in a baryon fraction of only 11% within R200 of MKW4. Now, this baryon fraction is significantly lower than the cosmic baryon fraction of the universe, and which is shown here with these magenta and red lines, and this is obtained from the Planck collaboration and the WMAP data. And this lower baryon fraction basically implies the 2 possible scenarios for MKW4. One could be possible that the central Asian feedback or galactic winds may have expelled much of its hot gas at its early epoch when it was a protocluster state. Or another scenario could be possible that the hot gas associated with these individual galaxies in the MKW4 may have cooled out of the intercluster medium and reside in the circumgalactic medium of the individual galaxies in form of a cold gas, or both scenarios could be possible. So now in both cases, you can understand that the amount of hot gas goes down and the ICM goes down, and which results this lower baryon fraction for MKW4, what we see here. Now, sorry. Next, we compare the gas mass fraction of MKW4 within R200 with the other groups and clusters with different masses. So here, the x-axis is the temperature at R200, and this is the gas mass fraction within R200. Okay, so now you can see that the gas mass fraction of the lower mass clusters or groups that always stays below the cosmic baryon fraction. However, the intermediate and higher mass clusters, they more or less consistent with this cosmic baryon fraction, this red line and the magenta line. And this basically implies that the gravitational potential well may plays a crucial role in retaining the hot gas inside of the cluster. Now, okay, so as we measured the gas properties of MKW4 in three different directions, here in this plot, what I'm trying to show you, the azimuthal variation of those gas properties from the average value. Now, our measured azimuthal variation for MKW4, which is this magenta data points, they are always stay below the 20%. So, and numerical simulations, they show that the 10% azimuthal variation is possible in gas density and temperature at R200 for the relaxed cluster, and 50 to 80% variation in the gas density and temperature at R200 is possible for part-up clusters. So our result, the obtained value for the azimuthal variation for the MKW4 are consistent with the numerical simulations of relaxed clusters. So this basically concludes that MKW4 is a relaxed group, and hydrostatic equilibrium is still a good approximation even out to its virial radius. Okay, so our this work for MKW4 has recently been published in MNRS. So if you want to go into details of our findings, you can please go ahead and check this paper out. Okay, so now for the next phase of my talk, I will show you some results on the metallicities of two galaxy groups, MKW4 and Antilia. So the Antilia is the nearest non-cool core galaxy group at a redshift of 0.009. And these are the Suzaku and Chandra mosaic image of Antilia. And you can see that, so we observed MKW4 in three different directions, but Antilia was observed in only one direction, in the east direction. And similarly, like MKW4, we use the Chandra observation to constrain the cosmic X-ray background. And here, these small ellipse or the circles, they actually, in the Chandra mosaic image, they are actually the result point sources. Now, these are the temperature profile and entropy profile of Antilia, which was taken from the Ong et al. 2016 paper. And this left figure, this is the temperature profile of Antilia. And you can see that X-ray observations show that Antilia core is approximately isothermal with a temperature of around 2 keV. And this right, sorry, so this right plot is the entropy profile of Antilia. And you can see that around R200, the entropy is agrees with the self-similar entropy value, which is this magenta line. And also near the center of the Antilia, the entropy profile is elevated. And this entropy profile is very much similar to the MKW4. So the similarity of these entropy profiles at the outskirts of these groups actually motivate us to analyze the metallicity of MKW4 and Antilia together. So here in the left-hand side, I'm showing that the average iron abundance profiles of MKW4 and Antilia. These blue data points are for MKW4, and these green data points are for Antilia. Now, we find that the profile for iron abundance profile for MKW4 shows a clear negative gradient with a supersolar iron abundance at the group center, but the Antilia shows a nearly flat iron abundance after this radius. It is about 0.05 of R200. And this happens because of the dynamic state of the center of those group itself. So MKW4, as I showed you earlier, that it is a relatively undisturbed system. And this basically helps MKW4 to maintain the higher metal abundance at the group center. But that is not the case for Antilia, because the Antilia is a non-cool core galaxy group, and frequent merging events may disturb its core, and which basically leads to a flatter iron abundance profiles, or flatter metal abundance profiles. So I will show you different metals a little bit later. Now, near the outskirts, you can see that both groups show similar uniform iron abundances of 0.2 to 0.3 solar abundances, and this agrees well with with past works of other groups and clusters, which also showed that at the cluster group outskirts, the iron abundances are about 0.2 to 0.3 solar abundances. But unfortunately, at the R200, um, for the Suzaku data of MKW4 and Antilia, they have insufficient exposure time to measure their metal abundances individually. So what we did, we actually fit the spectra at the outskirts of two groups together, assuming that they have similar metal abundances at their outskirts, and which is this purple data point. And while we are fitting these two spectra, we actually let the temperature to vary. Uh, Okay, so the right-hand side, this figure shows the iron mass to light ratio as a fraction of radius, and we compared the iron mass to light ratio of Antilia and MKW4 with other groups and clusters, and the red one here represents the Antilia, and the black one that represents MKW4, and this orange one here is the iron mass to light ratio for Perseus. Now you can see that iron mass to light ratio for both groups are increasing from center to the outskirts. And this basically signifies that the gas masses that are more extended than stellar masses in both groups. But near the R200 for both groups, they have iron mass to light ratio that is systematically lower than the Perseus. And this is because the star formation rate in the massive galactic clusters are significantly lower, and which makes the iron mass to light ratio for massive clusters a little bit higher. So here are the abundance profiles of other elements for MKW4 and Antilia. So the blue data points are for MKW4 and the green data points are Antilia. And these purple data point at the outskirt regions that I just mentioned, that we get these data points by fitting the MKW4 and Antilia at the outskirt regions together. So for most of the elements, you can see that Antilia shows a nearly flat profile after this 0.05 of R200. Okay, so next, what we did, we estimated the supernova 1A to total supernova number ratio. And these red data points in the left plot are for the Antilia, and the cyan data points in the right plot are for MKW4. And this green shaded region is the supernova 1A ratio for a large number of galaxy groups, and that are taken from Marnius 2017 paper. Now, Marnius 2017 paper only reaches up to R500, but in our work, we successfully extended up to R200 for MKW4 and Antilia. Our analysis, we extend up to R200. Now, this supernova 1A ratio is very important because most of the alpha elements like oxygen, magnesium, the neon, they are mainly produced by the core collapse supernova, where the iron peak elements like iron, nickel, chromium, manganese, they are primarily produced by the type 1A supernova. So supernova 1A to the total supernova ratio that helps us to understand the metal enrichment processes in the ICM. Like several recent studies, like Marnia 2017, they have shown that the uniform supernova 1A ratio near the cluster outskirts, So which basically rules out the pure core collapse supernova enrichment at the outskirts. Now, in our work, we find the outskirts of the both groups, they are consistent with the uniform contribution of both supernova in the metal enrichment of the intercluster medium of both groups at the outskirt regions. Because we did not see any clear increasing or decreasing trend in the supernova 1A ratio at the outskirts. But of course, these kind of trends may be hidden behind these large error bars because our error bars are large. But one thing you should notice that our error bars are systematically lower than the Marnier's work with 44 galaxy groups and clusters. Now, to proper understanding of the supernova contribution to the metal enrichment, one need more exposure to reduce the error bars on the abundances. Now, I think that the future generation X-ray mission like GRISM, we can actually measure the abundances at the group outskirts more precisely. So here is the summary of my talk, and thanks.
All right. Thank you, Arnab, for a great talk. We have a few minutes for questions. So if you have any questions, please raise your hand or put the question in the chat. And we have one raised hand, Stefano Andrion.
Yes.
Sorry if I didn't pronounce that correctly.
But you come back on the last point of your summary, because it's written that gas masses are more extended than stellar masses. Now, I work regularly on deriving gas masses and stellar masses, and I have no problem to derive stellar mass up to 2 R200. Instead, going way beyond 500 is very hard for the gas mass. So what do you mean with that the gas masses are more extended than stellar masses?
That because if we look at this iron mass to light ratio, so you can see that this is actually the R200. So in the R200, the iron mass to light ratio, that is kind of that's increasing function of radius. So that basically means that this iron mass to light ratio is defined as the iron mass divided by the stellar light. So as it is an increasing function of the radius, that's why we are saying that the iron mass is, the gas mass is more extended than the stellar mass. Otherwise, if the stellar mass is more extended than the gas mass, then it should be either a decreasing function or a flatter profile. That actually, I try to basically mean that a particular radius, the iron mass is more compared to the stellar mass.
Okay, thank you. Any other questions? We have like maybe a minute more, as our speaker does need to leave soon.
Yeah, I can stay here like 5 minutes. So yeah, I mean more than 5 minutes.
Uh, yes, I see Brian.
Yes, thanks for the talk. So I was wondering, so you were saying that the feedback from stars and AGN could be affecting the distribution of gas in the galaxy. Is there any way to like better differentiate and constrain the contribution from either energy deposition from either AGN or stellar winds?
I think from this current, so that's a very good question, Brian. So actually, from this current analysis, actually we cannot distinguish between that which is come from the AGN and which is come from the 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 galactic winds, because if you look at our if you look at the gas mass fraction profile, you can see that there is a clear discrepancy, and this basically hints that these this Asian feedback or the galactic winds, which drives the hot gas out of the galaxy group, happens before it has been assembled as a galaxy group. So it's kind of when it was a proto cluster state, you can say proto group state. It happens then. So I think from the current analysis, it's very much difficult to say that which is coming from aging feedback and which is coming from the supernova or star formation feedback.
Sorry, I was muted. Okay, thank you. Any last questions? Well, if you do want to discuss things further, Arnab's schedule still has a lot of open slots for today and tomorrow. So please go ahead and sign up. And welcome to the CFA again, Arnab. And now on to our second speaker.
Thank you so much.
All right. Yes, so our next speaker is Satoru Katsuda. He's an assistant professor at Saitama University in Japan. He's been interested in observational studies of supernova remnants, particle acceleration, solar flares in the corona, and Earth's atmosphere. He's also been an active contributor to Japanese X-ray astronomy satellites, including Suzaku, Hitomi, and Chrism, contributing not only to the scientific activities, but also to satellite operations and calibrations. Please begin when you're ready.
Yes, thank you for the nice introduction. And first of all, I'd like to thank Federico Fraschetti for inviting me to this seminar series. And I am really happy to give a talk. Okay. Okay, let me start. So today I'd like to talk about the origin of neutron star kick. And this talk is based mainly on my 3 years ago paper. Okay. As you may know, neutron stars are high velocity objects, and their velocity, their mean velocities is about 200 km per second, which is an order of magnitude larger than that of the progenitor massive stars. And the left-hand panel shows the proper motions of galactic pulsars and proper motions for I guess 1 million years expected for 1 million years. And the right-hand panel shows the histogram against the transverse velocity, and you can see peak around 200 km per second. And this high velocity is most likely or undoubtedly due to kicks during supernova explosions. But the problem is that we do not know the kick mechanisms. And there are two competing kick scenarios. And one is a so-called hydrodynamic kick scenario, in which supernova explosion asymmetry kicks a neutron star. And in this scenario, we expect more supernova ejecta is distributed against the neutron star kick direction. And on the other hand, alternative scenario is the so-called neutrino-induced kick scenario, and in which anisotropic neutrino emission kicks the neutron star for momentum conservation. And in this scenario, we expect more supernova ejecta in the same direction to the neutron star kick direction. So these two competing scenarios predict completely different observational properties about the ejecta and the neutron star position. And these two scenarios can be discriminated between by observations of supernova remnants. For this purpose, supernovae cannot help because supernovae are point-like sources, and we do not know the position of neutron stars. And only supernova remnants can help us because it's diffuse nebula, and we can study detailed explosion morphologies and locations of neutron stars. And there's a nice pioneering work by Holland-Ashford et al. 2017. And they basically found anti-correlation between X-ray distribution, X-ray emission in supernova remnants, and the neutron star kick direction, which supports the hydrodynamic kick mechanism. But however, there remained some caveats. For example, X-ray emission consists of both circumstellar medium and supernova ejecta components. And ideally, we need to separate these two components, and we should focus on only ejecta components. And also, the neutron star proper motion measurements seem too accurate. Probably because they did not consider the systematic uncertainty, I mean, astrometric uncertainty in measuring the proper motions. And then, meanwhile, at the same time, we were performing a similar, but hopefully somewhat detailed analysis of supernova remnants, in which we revealed the ejecta distributions, focusing on intermediate elements, including silicon, sulfur, argon, and calcium. In this analysis, we selected these 6 supernova remnants that pass the following 3 criteria. First, they should be relatively young, less than a few thousand years old. And second, they should show intermediate elements. I mean, K-shell line emission from intermediate elements in X-rays. And third, they should host neutron stars within the remnant. And so these SNRs that passes all the 3 criteria are only these 6 supernova remnants. And then what we should measure are explosion sites or SNR's geometric center. And this. And also we should measure the center of ejecta mass. And also we should measure neutron star positions, and if possible, their proper motions. And fortunately, we already knew precise locations of the explosion sites for these 3 supernova remnants. They exhibit fast-moving, optically emitting ejecta nodes. And yeah, you can see arrows. The proper motions of oxygen-rich fast-moving nodes can be seen as arrows in these panels. And by tracing back these proper motions, we can infer the location of explosion point, expansion center. And this is the very accurate explosion site. And so we used these already measured explosion sites. As for the other 3 supernova remnants, they do not show optically emitting fast-moving nodes. So we infer the explosion sites based on X-ray boundaries, X-ray morphologies. Briefly speaking, we measured the center of X-ray boundary at the various rotation angles. And we took the average of the geometric center. We calculated the geometric average. And we assumed the geometric center is equal to the explosion point. And as for the center of ejecta mass, a conventional method is to perform spatially resolved spectroscopy. In this method, we divide the field of view into small regions like this, and took the X-ray spectra from each cell, and then feed the spectra with a thermal emission model, basically consisting of swept up medium and ejecta component. And then from the best fit parameters, we generate the ejecta map for each element, like silicon and iron. This method is very, very nice, and but the problem is that it takes too much time. So we need to develop a more efficient way to measure the ejecta distributions. So we did it. We developed a new technique to decompose X-ray images into several individual spectral components, like circumstellar medium component and ejecta component. And to this end, we first prepare narrowband images, X-ray images. Here we divide the X-ray band from 4.5 kV to 7 kV into 40 bins logarithmically. And these images, in principle, provide us with X-ray spectra for every single pixel. And on the other hand, we also prepared template spectra for characteristic spectral component, like intermediate mass element ejecta component in black, and ion-rich ejecta component in red, and circumstellar medium component in green, and synchrotron component in blue. And then we fit each pixel's X-ray spectra with a mixture of these characteristic components by allowing the normalization to be free, only normalization to be free. And then we estimate the contributions of individual components in each pixel. Then we can estimate we can derive intensity map for individual components. And this is a result for showing intermediate mass element ejecta distributions for these 6 supernova remnants. And based on these maps, we calculated the center of ejecta mass as shown in these dots. Then you can see high asymmetric ejecta distributions for like PAPS A and G292 and N49. And then here we show we compare the positions of center of ejecta mass, intermediate element mass, and center of expansion or center of X-ray boundary, and neutron star positions for the 6 supernova remnants. And you can see that all the 6 remnants show anti-position. You can see the center of mass is in the opposite direction to the neutron star with respect to the center of explosion for all the 6 remnants. And the right-hand panel summarizes their relative positions, and you can confirm, you can check the anti-correlation between the neutron star and the center of ejecta mass. And this result clearly favors the hydrodynamic Higgs theory. And as a future work, I'd like to pick up possible correlation between neutron star kick velocity and magnetic field. Yeah, this correlation has long been discussed, but so far no clear positive correlation is found. For example, magnetars, the velocity of magnetars are perfectly normal, about 200 kilometers per second. But it's interesting to note that the so-called CCO pulsars, central compact objects, whose surface magnetic fields are about as low as 10 to the 11th Gauss, may be fast moving. For example, Papi's CCO is moving with a velocity of 760 kilometers per second, which is very fast. And also, Cassay's CCO is most likely moving at this velocity. This is also fast. It's interesting, but so far the number of samples are only 2. So it's important to increase the number of samples for CCO pulsars. Then a good target to measure the proper motions is the CCO in Virginia. Yes, this CCO is shifted 4 arc minutes away from the geometric center. And so this indicates fast motion of this CCO. And in fact, we found positive indication of fast proper motion by using the existing Chandra data. And yeah, the position of the CCO in 2000 is around here. In 2009, it appears to be moving towards the northwestern direction. Yeah, and the proper motion suggested is about 0.08 arcsecond per year, which corresponds to about 300 kilometers per second, which is quite fast. But we cannot perform image registration for these 2 data sets because there are no other point sources within the field of view. So in order to reduce the uncertainty and get the firm conclusion, we need further Chandra observations. This is essentially important. And also, our next important target that we think is the CCO in RX 1713. Yes, this CCO is 5 arc minutes offset from the geometric center, and which also indicates the fast proper motion. And interestingly, we recently realized that this X-ray feature X-ray knot is a diffuse source with a head and tail structure. And our grating spectroscopy clearly showed strong nitrogen line emission from this knot. And our spectral analysis, my student revealed that the nitrogen is quite enhanced. So this is this shows the evidence that this is the circumstellar medium blown by the progenitor of RHK 1713. And interestingly, the symmetry axis of this structure points to the explosion SNR geometric center. And this result clearly suggests that the geometric center is likely the same position as the explosion center. So the CCO is probably moving from this position. Then we expect a large proper motion of this amount, which corresponds to the kick velocity of this fast, as fast as Papway's neutron star. And unfortunately, the current existing data sets do not show such a proper motion, but again, we need to perform image registration for a firm conclusion. And also we need further Chandra observations to test this this possibility that the neutron star is moving this fast. Okay, this is a summary of this talk. We performed image decomposition for 6 young supernova remnants that host neutron stars and revealed the distribution of intermediate mass element, rich ejecta component. And we discovered anti-correlation between supernova ejecta asymmetry and neutron star kick velocity for all the 6 remnants. And this neutron star and ejecta recoil argues for the supports the hydrodynamic kick scenario, which is a natural consequence of the neutrino-driven explosion mechanism. And finally, we pointed out that the CCOs may be fast moving, and which should be checked by future Chandra observations. And we hope you or the Chandra team will accept this idea. Thank you very much for your attention.
All right. Let's all thank Satoru for some really fantastic results from some really beautiful work. We have time for questions. If you'd like to raise your hand in the for a video participation, or if you want to contribute questions to the chat, we can read them aloud. I see already one question from Randall.
Satoru, excellent talk, really, really fascinating stuff. Couldn't you also phrase your conclusion? I mean, you could imagine that both processes are happening, that both there's a hydrodynamic kick and a neutrino driven. Could you look at this in terms of what fraction must be hydrodynamic in that case, or what the ratio of those two processes could be?
Thank you for your question. That's very difficult for me to answer. Yes. For example, we cannot fully rule out the neutrino-driven kick scenario. For example, because you can see relatively how to say, as for N49, the kick direction and center of mass, the angle between kick direction and the center of mass is almost 90 degrees, which is far from 180. So this may be indicating that the neutrino-driven kick scenario it is contributing to the neutrino kick, neutron star kick. But basically, hydrodynamic kick is playing a major role, I think.
Okay, thank you.
Thank you.
All right, we've got a lot more hands up than we usually do. Pat?
Hi, Satoru. That's nice.
Hello.
A question about the way that you identified the mass distribution of the ejecta. I might have not actually understood it exactly correctly, but it seemed to me that your technique actually kind of gives the center of gravity of the brightness of the ejecta component, not necessarily of the mass.
Oh, actually, we think we measured the center of mass because what we did is basically we fit X-ray spectra by this mixture of components, emission components, and then we can derive their normalizations. Then, as you know, we calculate the density, number density of IME-rich ejecta component for each pixels. Then, by assuming line of sight plasma depth for individual components, then we can estimate the number density of ejecta component. So
yes, but it requires that you make an estimate of the volume. But I guess maybe if you use the same volume to then turn around and estimate the mass, maybe that's self-consistent.
Okay, yeah, you're right. Yeah, we assumed the plasma depth to be almost uniform within the remnant.
So
I don't know.
Not clumpy.
Yeah,
okay.
It's not. It's an approximation. So
okay.
Yeah, in that sense, you may be right. We cannot. We did not measure. We did not measure the mass.
Yeah. Okay. Good. Thank you.
Yeah. Thank you.
All right. Next on our list is Thea.
Hello.
Hi, Satoru. Nice to see you and very nice talk. I have a quick question. So what I'm wondering is to what extent do you need to assume that for all of these remnants, all of the ejecta have been shocked, and to what extent could some asymmetry in the reverse shock interaction be contributing to the asymmetry that you're observing?
Oh, okay. Thank you for the question. Yes, that's the reason why we focused on intermediate mass elements. Of course, iron-rich elements are still cool. Much of the iron-rich component, iron-rich ejecta may be cool, unshocked, but most of the intermediate IME-rich elements should be heated by the reverse shock for all of the remnant. Based on the amount, the mass of the ejecta. We discussed that point in our paper, and I can't recall exactly right now, but we believe that
I can take a look also.
Sorry, we believe that most of the IME-rich ejecta are already shock heated, and that's why we focused on IME-rich ejecta component.
All right, we have another question from John Raymond.
Hi, Satoru. That was very interesting.
Hello.
I was wondering, a large fraction of the mass in some of these is in oxygen, which is very difficult to observe, of course. Is that far enough away from the explosion center that it wouldn't have as much of an effect from the asymmetry?
I'm sorry, I couldn't get your point.
Sorry. A large fraction of the mass can be oxygen in some of these, and that's very difficult to observe.
Oh, yes.
The question
right.
is whether it is so far from the center of the explosion that it is not, so it doesn't really take part in the asymmetry. The oxygen is mostly the outer layers.
Oh, yes. So, oxygen are not sensitive to the kick, according to hydrodynamic explosion model by Garhin group. So that's also why we focused on IME-rich elements, IME-rich ejecta component, and of course it's difficult for us to observe oxygen-rich ejecta in X-rays because of the interstellar medium absorption. So that's also another reason why we did not focus on oxygen.
Yep.
And
okay, thank you.
Thank you.
Do you mind taking one more question? We have one from Tyler, Holland-Ashford.
Hi. Yeah, so it's a quick question on the neutron star in, I think, your last slide, RX 1713. You say that there is current data sets don't show such a large proper motion. Does this mean that current data sets show a small proper motion, or just that the current data isn't good enough to get any velocity estimate?
Actually, the current data do not show significant proper motion. I think there are two data sets, 2001 and 2005 also, and their position exactly matches actually. But we did not, at this moment, we did not perform image registrations. So, and also, so therefore, we should include large systematic uncertainty about 0.5 arc second. So at this moment, we cannot rule out large proper motions as well.
Okay, so you said the baseline was only 4 years between the images?
Yeah.
Okay, yeah, that's not long.
Yeah, we need a longer timeline baseline.
Okay, thanks.
Yeah, thank you.
Right. Thanks again to Satoru for an excellent talk, an exciting talk, and for joining us 13 hours ahead of us. It's very late where he is, so we are all very grateful. And hope to see you all again next time.